All right, so in the last video, I talked about the motivation for the cross product. In this video, I want to show you that what we get out of the cross product really is perpendicular to both of our original vectors. So just as a reminder, the cross product can be thought of as the determinant of a 3 by 3 matrix written out like so. Or you can just jump straight to the formula if you like to do that. For me, because determinants are something that I used when I was doing linear algebra, it tends to be easier for me to just memorize that it is a determinant than to memorize the new formula. If this is sort of your first time working with determinants, you may not find that easier, but eventually I hope you do take linear algebra and then you'll see a lot of determinants, and so you'll be used to doing it this way. So there is my A cross B. And so the claim I'm making is that, here's the claim, that A cross B is perpendicular to A, and A cross B is perpendicular to B. I really only need to show you the A value or the claim using A, because once I do that, I hope you'll be able to see how it's the same darn thing written out with B. So I want you to think, what do we use to prove that two vectors are perpendicular? We use our other type of multiplication. We use our dot product. When two things dot product is 0, then they are perpendicular, or the caveat, or one of the original vectors is 0. So I should say when two non-zero vectors have a dot product of 0, then they are perpendicular to each other. So let's try to do it. We'll do A cross B dotted with A. We don't need to do it in both directions because the dot product is commutative, even though the cross product is not. So what does that mean? Here is the first component of the cross product. Here's the first component of the cross product, and here is the first component of A. So I'm going to do A2B3 minus A3B2 multiplied by A1. I'm going to add then the next piece, because the dot product just says you do x times x, y times y, z times z. I'm going to take this, except for I'm going to apply the negative. So if I apply the negative, it's going to look like this. Negative A1B3 and positive B1A3 times the y value of A. Then I have the z value of the cross product times the z value of A. Now I want you to just pause for a second. If I was trying to prove the second half of the claim, what would be different? My A1, A2, and A3 would just be a B1, B2, and B3. Remember, what's the goal? If the dot product equals 0, then I have perpendicular vectors. So let's distribute and hope everything cancels out right. A1, A2, B3 minus A1, A3, B2, done with the first part, plus, I guess I could have written minus A1, A2, B3 plus A2, A3, B1. I'm just putting the A's in front of the B's to make it easier to cancel things in a second. Then I have A1, A3, B2 minus A2, A3, B1. And I'm trying to keep them in alphanumeric order. All right, let's look. Here's an A1, A2, B3. A1, A2. Here's an A1, A2, B3. Positive, negative. Next, I've got an A1, A3, B2. Here's an A1, A3, B2. Positive, negative. Last, I've got A2, A3, B1. Here's an A2, A3, B1. Positive, negative. I hope you can see how the exact same form, proof would work, replacing the A1, A2, and A3 with a B1, B2, and B3. Works exactly the same. And so, because A cross B dot with A equals 0, theta equals 90 degrees. Because remember our dot product definition. Our dot product definition is that A dot B is magnitude A times magnitude B times cosine of theta. We're claiming that A and B are non-zero. Therefore, this is not 0, this is not 0. So the only option then is that cosine of theta has to equal 0. If cosine of theta equals 0, remember back on our unit circle, if cosine theta equals 0, you're sitting up here. That's a 90-degree angle right there. Or you could say pi over 2 if you're more of a radian person. So, same proof would work for A cross B dotted with B. Same proof would work if I did A dotted with A cross B because the dot product is commutative. So this is a really useful thing. The cross product gives us a vector that is perpendicular to the original two vectors.